So one of the things that complements this course was that talk on computer modeling from Dr. Duffy. Love that guy, by the way. If you ever had a chance to take his classes over in IE, I think you'd really enjoy it because it complements this, as well as Dr. Proctor's class. But man-machine systems really ties in very nicely with this concept of computer modeling and so on. But where this also migrates to a little bit is Dr. Proctor's class when he talked a little bit about how we respond to stimuli. And then the idea is how its form and function. And there's some fun things that I want to share with you in this lecture about that. One is that everything that we do is a measurement of risk, right? And there's no risk-free day on anything that we do. It's just the wrong place at the wrong time. It just crazy stuff. And I just saw some disturbing stuff on the news this morning about a new thing called One Punch or something like that, where basically you got these little gangs running around sucker punching innocent people, men and women, not suspecting it, and the idea is to knock them out with the first punch and get some thrill from that whole thing. And so you could be walking along doing everything right, and then just someone comes out of nowhere or sneaks up behind you and gives you a sucker punch, tries to knock you out. And it's very disturbing, this new thing going on. Apparently it's happening all over the country, including Chicago. But the idea is that we know what are your risks and always being aware, right? Being in the moment and knowing what's going on. So it's interesting, when I was down in Orlando giving a presentation with the peri-anesthesia nurses group, it was at Disney World in the Epcot Center. And they're essentially doing the same thing, but they're doing it with a bunch of chairs stacked up in front of a building. Certainly not up in a windy high-rise like you see right here, where all these daredevils would go out there and do this kind of thing. And there's not a lot of fakery in this picture. There people would actually do this and try to balance themselves out there. And if they fell to their peril. So the idea is that always know your risk and be aware of that. And in doing so, the idea is that how do we process information? Because processing information can be very simple to some people, but then there can be very complex systems behind it. So for example, many of you, when you go out to your cars, if you have a car, or you know someone who has a car and you drive the car, the idea is you get in the car, your key turns on in the ignition, and it just gets you to where you want to go. So you have input, fire up the engine, get to where you want to go, and there's your output, basically a response of getting you to from point A to point B. Anything under the hood is like a black box. They said, who knew the thing needed oil? Like who knew it needed water? My God, I don't know. I've never looked under here, right? Because cars have gotten so reliable. So it's basically, to many people, systems work in a black box kind of process, but there's a lot more going on inside that black box. And that's the whole idea of what we do. We have to figure out what's involved. We want to keep it simple, keep it as simple as possible, but we have to fully understand that process. So in doing that, we have an action result feedback system where the idea is that the worker or the person input information, you have an action, and the machine reacts to that action. You get a result, and then that gives you feedback to you again, and that completes the loop, right? So there's any number of processes that we're looking at. My lecture alone is basically, here I am, I'm your worker, right up here. My action is to give you a presentation. The machine is the projector by being able to give you this display. The result is, hopefully you're learning from this, and it feeds back to me, and then I continue the process to the next slide. So when we get into more complex systems, what we see is that we're looking at environment, and materials. We have something very simple right here where we have the machine, we have the effectors, the changes, we have our controls. This could be like a gas pedal or a brake that's giving us feedback. We're sensing the environment, we're putting that information that goes into that change. The machine could be the engine, for example, and as we're going down the road, it's giving us sensory feedback so we stay on the road. Very simple system. Now we're going to add to that information where maybe we don't see the road, and now we're looking at not only a visual aspect, but actually we're flying what's called fly-by-wire, right? So one of the things that's been in the news lately is that many of the pilots that we trust our lives to have become so dependent upon the computers flying the airplanes, including takeoff and landing and so on, they are not sensing where they are or they're in trouble. And so we're starting to see more crashes at airports and so on. One of those that occurred out in San Francisco, right, where the plane came in from Asia, and they're pretty much flying by wire, and they came in too low and too slow, and they basically hit the edge of the tarmac and busted off the rear of the plane. I think 2 people died in that, and one of the people that died was basically she was alive, but because of all the debris and everything, some rescue truck ran over her and killed her in the process. But the idea here is that we're going by displays and sensors now rather than visually seeing things. So it gets a little more complex in that regard, and then we add to that the idea of displays and sensors, and then we bring into a computer to modulate everything. And all that information now gives us a process and a feedback where this, bringing in the computer now, gives us the quantitative information that we need in order to make decisions about go, no-go. These are the simple symbols that are used in terms of functions and analysis, decisions and choices. Notice the differences in the endpoints. Things the operator and persons or processes are going both ways. Or knowledge or information. And notice that the taper on this end here in terms of the change. So these are the simple systems that we can use. Instead of writing it out, just use symbols, right, to be able to explain a story. So in this case, we process that. We have our designer right here. We have a system specification. That goes to a producer. The producer gives us a product and develops a manual. And I talked a little bit about this, and in fact, manuals have gotten so much better over time, but we still get these manuals that are written where English is not the first language, and you're trying to figure out what in the heck are they saying, because by the time it's all said and done, it's like, I got 3 or 4 extra parts here. You know, it's like it's supposed to be assembled. Well, did they give me extra parts, or did I screw up? And you're looking at the instructions and the manual and the diagrams, and they just don't come together very well at all. So the idea is that from that producer, not only do we have a product, but we have a manual that shows us how to put together that product. And then, of course, here we are. We're the assemblers on this end here. And then what's the experience from that process? It was basically thumbs up or thumbs down. And then that goes back to the designer and say, well, we need to improve on this. And one of the things that I've seen, especially in your generation, that I didn't see a whole lot in my generation, especially on the software side of the equation, are early releases of software that's really not quite ready for prime time. And next thing you know, you're getting all these patches. So, and this is not meant to be political, but it sort of comes out that way, and I don't mean it to be. The whole Affordable Care Act online system, right? What a disaster. It's unbelievable that we didn't use the talent that's out there to put this thing together right on the front end. But it becomes so much the norm to go ahead and just push it out there without being ready to go that it's okay if we do patches and fix it up, so on and so forth. In this case, because it impacts on so many people and there's so much skin in the game, there is a lot of pushback and a tremendous amount of pushback from people like you, because you're the ones basically carrying the system. Chances of you breaking down are much, much less than someone like me. So basically the idea is if we get you in there, you subsidize me. Should I have some issues? Like, you might be thinking, well, the heck with you. Well, the idea is that when you get to be my age, you'd like that same thing handed off. So you're basically paying it forward, if you will, right? That whole thing. So what I'm seeing more and more now, and it goes back to the designer, is that pushing it out too soon can result in some very negative consequences and outcomes. And, of course, we see that as it's being played out on the news daily with the Affordable Care Act website. So system design process, notice that it gets a little more sophisticated. Our specs, our functions, allocation of those functions. And notice over here we have design and personnel and design of the hardware. And the idea here is on the software side, and this is on the hardware side. Kind of interesting. Anyone who's interested in mechanical engineering, one of the first things they're going to tell you, are you interested in software or are you interested in hardware? If you want to get a degree, advanced degree in mechanical engineering. And if you're not thinking about that actively, say, well, it doesn't make sense. Mechanical engineering to me has always been about the hardware. And said, no, there's a tremendous amount involved with software in terms of mechanical engineering and design. So keep that in mind. And it all comes out here in terms of the interface, the user, and most of you know about that, right? The user interface system. And then you finally commission that system, basically roll it out when it's ready and people can use it. So it gets more complicated now in terms of now the human factors side of the equation. Notice we have design and we have operations. And notice as we go down on this side here, documentation, success, functioning, separation, internal communications and feedbacks, performance, critical incidents, and accidents, all part of the design process. Over here in operations, we have information processing and training. Training is critical, right, to make sure that the more training has gone on over here, the idea is that it's going to give you some feedback about the design process. But then as you go through this, you have task analysis in terms of how complicated it is. Then you have simulations. But down from this process here in the information presentation, you have the plant interfaces in terms of how it's going to come out for control rooms and so on, all the way down to support, to the instructions. And again, this is about the manual, operations, maintenance, supplies, safety, energy, and over here, online, offline evaluation in terms of how this is going to work regarding the training aspects of it. Not only by the users, but those that do the maintenance and updates and functioning. So this is one of my favorite slides. I'll hold you responsible for this, so make a note there on a couple of things. And this is really the difference between machine and the person, right? So if we look at the attributes, speed, power, consistency, informational capacity, memory, reasoning, sensing, and perceiving, that for the most part, we get trumped by machines. But it's going to be a while yet. I think the magic number is something like 2050, where finally you reach that tipping point where the computer now has all the sensing capacity and capabilities and thought processes as we do. In fact, I think there's Time Magazine just came out with a front page article about where that tipping point is between computer and man. But right now, the machine, in terms of speed, is superior. We're pretty slow. We go in seconds. They actually go in milliseconds and faster. In terms of power output, they're much superior in level and consistency. We're kind of weak. We have our spurts of energy at about 1,500 watts to less than 150 watts over a workday. And right now, in terms of here, energy output, you're pretty close to the other end of it. Your mind may be functioning, but in terms of energy output, it's lower. In terms of consistency, ideal for consistent, repetitive activity. No, I don't know what I'm doing here. I don't know why that's here. We're not very reliable, always subject to learning and fatigue. Informational capacity can be multi-channel. I'm multi-channel. I can do more than one thing. Believe me, you cannot multi-channel. If you're looking at your computer right now, it's something else. What you're doing is you're sharing, you're flipping back and forth with me. Whatever it is you're looking at, or you're texting, or whatever you're thinking about, is that you're flipping back and forth with me and only picking up bits of words and sort of assembling the information together while you're sharing me with this other information. There's no way that you can hear me and process information at the same time. We are not multi-channel. We are single channel, but we have the ability, we've learned, to flip back and forth on that. Some of us become more skilled at that than others, but I can tell you that sometimes a critical thing can be said when your mind is on a different channel, and if you miss that, it can make a difference. So you have to always make sure it says, what's my priority right here? What channel do I always want to be on? And if you have to switch to another channel, which one of those weighs more in your priorities? And whatever it does, that's the one that plays out in terms of you remembering things. So you have single channel, low information transmission rate, usually about 10 bits a second. And of course, computers go, actually now up to gigabits, right, in terms of processing. Memory, ideal for literal reproduction, access restricted and formal. In other words, there are bytes and bits involved in this in terms on-off, black or white, that kind of thing. We tend to be a little more on the judgment side of thing. We're better for principles and strategies, access, versatile, and innovative. So the idea is that we are able to, through our own mental processing experience, have a gestalt kind of thought process in terms of a cumulative amount of information coming into us versus the information that is hand to what the computer has to make a decision to. Reasoning and computation, good deductive, tedious. You have obviously programming is involved, but it can be fast and accurate, and poor at error correction. In other words, once it's wrong, if it's programmed in wrong, it's wrong. So 2 plus 2 we know equals 4, but if it's programmed in wrong, it's never going to equal 4 in the computer. So we have to make sure that that programming is correct. For us, good inductive reasoning, easy to reprogram in terms of, okay, you got that wrong. For example, on our clickers, we get that immediate feedback and so on. Those that have a spread in terms of the answers, A through E, and they say the dominant answer was C, then that quick feedback means it's basically going to help us in terms of reprogramming our thought about that answer and say, oh yeah, now we know it's C. We're not going to do that again if I see it in the future, and chances are you will. So, but we are slow. We're not very accurate, but we are good at error correction. In other words, if you know it's C and you see that question again, you're not going to answer B, right? You're going to answer C. Computer won't be able to figure that out. It's not if it's not programmed properly. Sensing, specialized and relatively narrow in range, good at quantitative access, poor at pattern assessment. Although we're getting better and better about that, right, in terms of face recognition programs and so on. We're really good at that, and they're basically, there's some people out there, and we still beat the computers now. Scotland Yard, there was a piece that came out that talked about people who have high sensing capability, where they can look at facial features and they can see a picture, and they just have a mind for it in terms of separation of the eyes, certain profiles that stand out, and so forth, and they can see actually kind of a blurry image. Try to bring it into focus a little bit, but match that up. Computers can't do that yet. They can only do it if it's like, boom, a straight shot like this, and then match it up with all the other features that they have in their inventory. Still beat them on that, but we're not too far away where the computers are going to get just that good. But we are poor at the quantitative side of things, but we're good at pattern detection and interpretation. Perceiving, poor at coping with variation in written and spoken material, poor at detecting messages in noise. And when they mean noise, signal from noise. What thing is important to us and what things can we dispense with in terms of background? We are very good at coping with variation in written and spoken material, good at detecting messages and noise. The idea is that, for example, a written and spoken material for international students, even though English isn't the first language and they may not recognize all the words that I'm saying, they can interpret better than if you were to basically take what I'm saying into a computer which is not using English as a primary language and basically word for word come up with what I'm saying. So there's where the pluses and minuses are. Make note of that in terms of where we're better and where the machines are better. So obviously on the quantitative side, the machines are better in terms of information processing. If it's quantitative, it's better, and so on. But we are better at the collective reasoning and processing of information compared to computers today. These are faults, indication, and likely causes, and it goes from the routine to a disaster. So, for example, looking at a single component, for example, changes in pressure and voltages and so on, this is just a routine malfunction. And what I'm going to do is I'm just going to have you do the spread like I've done before, for example, on the vibration side of things. Is you just look at a single component, go all the way down to strange pattern of failures. Indications which suggest that the plant is fighting the operator, deliberate expert damage, in other words, sabotage. So we go from a simple failure, it might be a blown fuse that we can fix, to something that we basically have feedback and patterns that just don't make any sense to us at all, and you can point to a number of things. Probably one of the most famous in the literature is the 3 Mile Island disaster, where people were just basically, punching. They thought the right buttons in order to control from a possible meltdown and indications of shift the plant is fighting the operator. They weren't believing what they were seeing because they were the system was trying to override theirs. And so what happened is, as is deliberate, expert, or damage, it basically, they, unbeknownst at the time, were doing damage to a system that was trying to protect them. Very interesting. So it doesn't always have to be sabotage. It can just be they've never seen this before and reacted in such a way that the computers now were fighting them in terms of controlling the nuclear process. Displays and controls. The statuses of machines are through displays. Obviously, humans interpret these displays. They interpret these displays by mentally processing, perceiving information. Then you make a decision, and you convey the decision through controls. We have direct and indirect. So all of our direct sensing would be touching a hot stove. What you feel in terms of comfort level in this room. Is it too hot? Is it too cold? Is it just right? Indirect is a gauge. So while I'm feeling and sensing the temperature in this room, I can go over here and look at this thermostat, and man, it is warm in here. The guys are saying, and the girls are saying, no, I don't think so. It's about, it looks, I don't know, to me it's got a little bit warm up here. It's about 76, 77 degrees, according to that thermostat. But that's what the temperature is right there, right? Not what it is back here. It's going to be different around the room. But there's your indirect, right? Gauge and signals and so on. So I'm figuring it's somewhere between 75 and 80, depending upon where we are in the room. And of course, we know why the ladies feel cooler than the men, or why the men are warmer than the ladies. And you knew this from my first lectures, and why is that? Why are the men warmer than the ladies, or feel warmer in the same environment? You know this. It's an exam question. Yes? Well, the metabolism is going to be a little bit higher, but what drives metabolism? I'm going to give you a suggestion. Right, cross-sectional area of the muscles, right? Muscle mass is typically larger in males and females. Not always, but it's a larger cross-sectional area. Because we have more muscle mass than women, we are going to be basically heating up more, and our basically sitting metabolism is going to be higher than the sitting metabolism for a female, right? Because of size, muscle mass, and so on. As a result of that, we're going to feel warmer than the ladies do. That's why there's always this tug of war with the thermostat, right, in terms of turning it up or turning it down. It's a fundamental thing that you should know when we start getting into these kind of things in terms of why it is the way it is, right? So understand those concepts, because by now these things should be connecting for you. Mechanical and electrical equipment, manual tools, following a standard set of procedures. Workers interact with equipment to produce a desired output, and then the workplace is serviced by facilities, waste removal, and so on. So this is a cycle, right, in which we go through for the characteristics. In other words, we perform work. We have tools to perform the work. There are standards and procedures that are in place to do the work. They interact with the equipment. There should be a layout or a protocol toward that end. And then there should be a maintenance process to that, because things do wear down. In terms of ergonomics and human-machine systems, design of tools to match the physical characteristics of the worker. And again, what I've emphasized from the very beginning is that this is not about differences between males and females. This is about raising awareness in terms of those differences and leveling the playing field so that everyone has a shot at what they want to achieve in the workplace. And that's what this whole idea is about. It's not about let's grab Josh, for example, because he's a big guy and we're going to have him move these big bales of heavy things from point A to point B. I said, well, why don't we get a vacuum unit and attach that up, and any one of you now here can just attach that to it and pick it up, bring it over here, and drop it down. Not only that, your production pace can be, you can figure out what your return on investment is, and within 6 months, you're going to have that machine paid for. And not only that, you can hire anybody that you want because the machine's doing the work. So that's the concept behind this. A lot of companies don't get that yet. Design of the workplace and workspace to meet physical characteristics. Design of controls and displays to allow the worker to operate and monitor the system processes. Development of job procedures that meet the worker's capabilities. And that's really the key right there, meeting their capabilities. minimization of effects of external factors such as noise, temperature extremes, vibration, and so on. Some of you are pretty good about drowning out the noise, but you like a certain amount of white noise, so like you'll study at, Starbucks or near a place like that. Or you just like super quiet where you can really hear your thoughts and you can think. Maybe a really quiet place in the library and so on. All of us have our thresholds right there, but the idea is that what's your comfort level in terms of minimizing those external distractions. Steps in design, objectives in terms of desired output, your input specifications, your materials, process description, functional allocations, interface design between the operator and the system components. This is form and function, just like you see right here. This is my interface in terms of basically what I'm looking at on the computer and what's being projected to you here. Facilitator design, mechanized assist, as I talked about earlier, and then testing and evaluation to make sure that the system works. Steps then are number one, prepare what needs to be done for the person to do their job. Observation, what information data does the worker have to do their job. Decisions and mental processes to do the job. So it's not just the physical aspects, it's also the mental aspects of it. Physical demands then, what are the physical tasks involved? And again, if they exceed most people, then the idea is mechanical assist, right, to level the playing field. And then termination, what steps do you need to complete the job? So in other words, what's called a work cycle. Okay, so remember this, because we're going to get into that, and I'm going to test you on it. This is the work cycle. There's not a test that I have given where I've not asked this question in various ways. And so the idea is that we start out and we define a job, right? So as students, your job classification is student, right? We'll just start out there. But then the next step down is what functions do you have throughout the day? Well, I get up and maybe your routine is to study a little bit in the morning, or maybe have breakfast and study a little bit in the morning. Maybe there's a workout involved, that kind of thing. You go to classes, then you have lunch, and so on. So maybe these functions that you have listed up here would be going to class, okay? And then the next step would be, what are the tasks with the function? The tasks are coming in, actively listening, taking notes. Maybe before that, you're going to burn off a copy of the presentation so you can annotate as I'm talking. And so that's the task of being. What are the elements? The elements would then be taking those notes to the specific slides that I'm showing in the slide deck. And then finally, the micro motions are putting little notes or asterisks there when Dr. McLaughlin stops and said, you really need to know this slide. And next thing you know, so the micro motion is, I'm definitely going to put some little notes right there, maybe some eyeballs. I love to put eyeballs in, because that would always, my colleagues at Yale who went to school with me at Michigan, and kind of make fun of me because I'd always go down something that was really important to me in terms of where the professor would come up and he would say, you really need to know this. I would always do one of these things right here. And if it was really important, I'd really start raising those eyebrows like, make sure you know that, make sure you know that, and that, and that, and then that too. And then I said, oh man, make sure you know the whole thing as it relates to the top to the bottom. And next thing you know, by the time I got done making all my notes and everything, it would look like that. And they made copies of that and sent it to me later. Anyways, and they'd ask for my notes. I was flattered they would ask for my notes, but it was actually having fun with me making all these notations. But the idea is that we start out with the job, we get into the functions. From the functions, we have our task. From our task, we get into elements. Elements are micromotions. Micromotions, as many of you know, if you've gotten into this business with industrial engineering, these are also called Thurbligs. BL, sorry about that. IG, Thurbligs. And actually, it spells Gilbreth backwards, right? And Frank and Lillian Gilbreth, they were faculty here over industrial engineering, and they were the ones to break all this down. Why is this important? Because the idea is that if you can go all the way down to micromotions and define those, and then start backing off, going up to the elements and so on, you can actually time how long it takes to do some things, and you can design jobs around those elements. Why is it important in ergonomics? Because if you can get down to third legs and motions, you can define what tasks put the worker at risk. And by defining those tasks, and you say, well, we can eliminate that task if we shift this reach right here by moving the part closer to the person. So now we've eliminated that. Not only that, we've saved some time, right? Because if I tell you my height, my stride, and so on, and you know the distance from here to the door, you can predict, if you do a watch without doing that, just knowing that the distance and pace is that 1, 2, 3, 4, 5, 6. Hit the door. Within 5 seconds or so, right, you know that I can be from the center of this room and to the door on a normal pace, right? Think about expanding that now to include all of these elements right here where you can actually lay out exactly all the things that I do, and you can have it timed and on paper. And then basically you can play that out and see how well that matches up. That's the reason why you want to know this particular slide, from the job itself, defined in the broadest category what it is, right down to the very specific tasks that you do that take up time. And the idea is to translate that to make a job safer in terms of identifying those elements. Also, micromotions, also called Thurblegs, and the Thurblegs come from Frank and Lillian Gilbreth. And the Thurbleg is spelled, and that's their thing. They came up with that. They thought they were clever. Must have been a late night with some wine where they came up with that idea. Yes? No. No. Not from the whole thing. Your job then breaks down in a work cycle is what is involved from the start of a particular function and not. So in this case, let's say a work cycle, depending on how you use it, and it's a fair question, is not this whole thing. No. It can be a function or a task depending upon how you define that particular work cycle. So a function would be going to class. You could call that a cycle, right? Because you come here, you take notes, the class ends, and you leave. Very defined beginning, very defined middle, very defined end, right? But you say, well, no, I really want to define a work cycle as a task, and the task is I've come to class, but is basically when he starts lecturing, once he gets off all of his tangents, and when he really starts talking about the content, that's going to be the cycle, and when he finishes talking about the content, that's going to be the end. So really to define that as a work cycle, it has to have a very defined beginning, middle, and end, not a title. Is that okay? Fair question. Good question. Okay, so we get into controls and counters. These are good just at a glance. You can see them. We can have fixed scale with a moving pointer going around, basically these things moving around in clockwise position. Or we can have a fixed pointer right here, and then this moves right here. This could be like weighing objects and so on. So guidelines for designing displays. Minimum amount of information needed to make a decision. You don't want too much coming in. Use digital readouts. Use circular or semicircular scales instead of vertical or horizontal scales. Avoid moving scales. Use major markers in a natural order like 1, 2, 3, not 2, 8, 9. Avoid multi-scale or multi-pointers. Too many things going on to process. Display should be in a direct line of sight by the operator. In other words, you shouldn't have to look up or look down, but straight ahead or up at an angle. So where that exit sign is located for most people is when you look at the layout of this room, for most of you, it's within the angle of your line of sight. Avoid glare, small size or illegible displays. And again, this is all about font, right? And I'm going to talk a little bit about that in a few minutes. Use capital letters for single word sentences. This can be seen from greater distances. Ta-da! Look at exit, right? You don't see those in small. You don't see a big E and a small, X and I and T. They're all caps. Heights and widths of major, intermediate, and major graduation marks should follow the guidelines that I'm going to show you now. And so this is where I'm going to ask you a couple of test questions that may become extra credit on the midterm. The idea is that read the small print on the bottom right here. See the 28 inches? for a viewing distance is what these marks are allowed for. And you have poor lighting and adequate lighting. See the difference between the two? So with low lighting, then obviously the size of the markings at 28 inches away, basically an arm's length away, right? That when you're looking at critical markings, positions, and so on and so forth, 0.2 of an inch, right, or about 5 millimeters. When you have better lighting, then it's almost half of that, right? So it's about 0.12 inches or 3 millimeters. Critical markings, position fixed. Here you can see 0.15, 0.10 in terms of low lighting, adequate lighting. Critical, non-critical markings, then it can be even smaller, 0.05 inches or 1.25 millimeters. For adequate lighting, again, 0.05 inches or 1.25 millimeters. So you hit a point here where if it's non-critical, it's not as important as you have the critical being the larger letters. So if we're looking at a situation like this, intuitively you know that the further away from this mark you get in terms of what I'm showing you right there, the larger the height and the width of the stroke has to be for the letters and the numbers. Is that right? Everyone good with that? So how would we figure out what the size is going to be if you're sitting in the back of the room and you still want to see what I'm showing you up here? In other words, if you see this in the back, of course it's a little unfair because you have, most of you have good vision, but the idea is that can we determine, based on the size of the font that you see right there, going all the way back here, is there a formula that we can use basically to look at that? And it doesn't, if you look at the small print on the bottom, it does get a little bit fuzzy. But say, okay, it's adequate for back here. Is there a science to that in terms of distance and size? Turns out there is. And the idea of that is that you take the distance, we're going to the back of the room, and that's in the numerator, right? And you divide it by 28 inches, right? We're going to obviously keep it in the English format. That product then is multiplied times the numbers that you see up there, the 0.2 inches, right? And that tells you what the size, the height of that letter display should be. And then in the next slide, right here, it also tells you about the width. The width in all cases will not be the same as in the height. It's usually a fraction of that. 5/6, 4/5, something like that, and you can see those numbers. I will not hold you responsible for memorizing these differences, but notice the critical factor is the height. And then the distance apart and the width of the letters and the numbers then are a portion, right, of that overall height. So remember that as we're going through and doing this, because you can basically determine how far back something is and pre-orchestrate what size font that you're going to have so that the people in the back can very comfortably see what you have without the aid of glasses. Is that cool? You can do that. It's like, oh, who knew? You know, and it's not, some people can do hit or miss, but there's actually a science to that. Same thing with strokes, keystrokes in terms of major marks and minor marks and so on, and distances apart. I won't hold you responsible specifically for these kind of things. Just remember that basically we're looking at the length of the stroke is our reference point, and then the distances between them and the shorter marks right here are regulated based upon the size. So, guidelines for warning. 1, size. Warning lights should be subtended at least 1 degree of visual angle. In other words, basically angled out so that you can see them easily. Color. This is your order of response. I'll hold you responsible for this. First red, then green, then yellow, then white, in that order. This is for eliciting a fast response. Okay? Flash rate. This is steady light attracting someone's attention. Optimum flash rate, check this out, 4 times per second. Who knew? Any faster, you get a strobe effect, right? And slower, and it's kind of on and off. But in order to elicit a human response, it turns out that 4 times a second gets our attention. So there's a science out there. Contrast with background, brightness and color enhancement. effects warning lights, multimedia presentations, auditory. That's one of the reasons why I have this little microphone connected to me so you can hear what I'm saying along with the slides. Because it's one thing seeing the slides, but it's another if you complement or marry my voice with that, especially because you can hear my pitch, you can hear my emphasis, and so on. More people can understand the information when you give it to them in multimedia. So controls and our layouts. Very quickly go through this, forward and back, side to side, on the front, in one direction, usually from left to right. Controls on the bottom would go up, always in a clockwise position. You notice that? In most controls that you see right here, very seldom do you see it going in a counterclockwise position. That's a test question. Almost all controls that we see move in a clockwise direction. Pointers going up right here, again, left to right, and then scales again going clockwise direction from left to right. In terms of system responses, this is a light button. When you press it, it lights up, right? So you get a light button. Rotary, as your arc, for example, if it's less than 180 degrees, you shouldn't be laying it out as like a compass. It should be laid out as a form that you see here, because it should make sense to you in terms of if you know this is 180 and you're only going to be showing something that's 120 degrees, it should kind of match, you know, what that degree or that angle is, right? And if it is truly a 360 going around in terms of through an arc, then you're going to have a full cycle going all the way around in terms of through that arc of more than 180. Linear dimensions, moving in one direction, is better. If it's got to move in two directions, an XY, then it's good to have a control stick. Switches, interesting thing here in the United States, turning things on, the light's up. Turning things off, the light is down. Off, okay, up. If you go to Europe, it's complete reverse of that. Up is off, down is on. You know, we have all kinds of other issues, all right? 110 versus 220 voltage and so on. But you have to pay attention to where you are. So this is a little more US-centric. Thank you, Mike. Rotation, again, notice a clockwise direction here. Movement, again, clockwise. Same thing with steering wheels. So when you turn right, it makes sense that you're going right. And the pedals, same thing, basically pushing down with the stronger. Most people are right dominant, so the stronger leg pushing down and the left one coming up in terms of looking at levers. Same thing with linear rotation with lever sticks and with rotational with rotary. This is another thing. So again, I'm not even going to get extra credit, but I want you to understand the idea of control response. And the idea is that how do I design a control panel so that if I'm moving a joystick, and many of you have experienced this on your controls for games and things of that nature. I'm not a gamer at all. Sort of missed that thing as I was growing up, but I know some of you are really good at this. Is how do they determine the size and height of the joystick and how much movement there's going to be versus what you see on the television, right? That you see ahead of you or on the screen. And the idea is that basically, what is that angle, that alpha? So the idea is that some of the questions would come out is that you can actually design, if you look at alpha as the angular movement of the control. So let's say that's your unknown, and you know that the length of this, that's your lever arm, that's your joystick, if you will, your display movement. This is the movement on the screen. The idea is that what you're basically looking at a control response ratio, you can solve for alpha in terms of how far you move that joystick in terms of degrees, right? So some simple algebra will help you resolve that. In this case, if we're looking at something that was about 5 inches high or so, that if you run the math on that, you're going to see that basically you're going to move anywhere between 2.5 degrees to one direction as a minimum in terms of response to 4 degrees as the most sensitive, right? Sensitivity on that. So you can do those calculations and solve for alpha in terms of stick movement, but you have to have all the other information there. You have to have D, you have to have L, and the rest of it's all right there in terms of control and response. So there is a science to that, and I just wanted to raise your awareness to it. And this is an example and an illustration. Consider this your game stick right here, and consider this to be your screen. Is how much movement is going to be here versus how much movement back and forth that we're going to see, whether it's a car or, you know, whatever it is the games do these days. And this is what it looks like. I will hold you responsible for this, and that is that when we look at gross adjustment right here, and this is very much like the best thing I can come to is that even on my car that I have now, it's a more modern car, is that you can have preset buttons, but you can also, you know, they got away from it for a while, especially with the Japanese cars. It was push button. Problem is they made all the buttons really tiny for the tiny Asian fingers out there, but realized, you know, Americans were buying these things, so I hated them because we have big fat fingers and we couldn't hit those little buttons. So they went back to a knob, right, to control for radio stations, and you know, you rotate until you hit the station that you want. So when I'm down in Indianapolis, I like 104.5. I don't know if maybe you've heard 104.5, but they have a variety of music, that kind of thing. When I'm up here, I believe it's 98.7 or 97.8. Anyways, one of those stations, kind of a variety of music there as well. I think the one down in India is a little more hip than up here. But anyways, the idea is that as I'm rotating from that's at 98.7 to the 104.5 as I'm driving to the airport, the idea is I'm moving really fast, right, all the way down to get to that 104.5. And so this is your time that's being used. And notice how fast that I'm moving right here. But then as I approach that station, look at the time element, you know, in terms of coming down right here for that fine adjustment until I hit that station. In other words, my control response right here, it shows me that I'm moving really, really quick to get to that station, but as I approach it, I have to slow down, right? And that's basically go from high sensitivity on this end to low sensitivity on this end. So you can go real fast right here, not very much time, and then you have to really slow down where you require more time as you get out there to fine-tune to that. So the idea is you have what's called slewing right here as the operation of the time it takes you to find what is the ratio of that dial on the radio to the size of the knob and how much you have to turn it in order to move it down, right? So there's a science to that. Even though it's all digital, it feels analog, and the idea is that you can calculate that exactly to what that should be in terms of size and movement. Because if it's too tiny, you can't get to it easy, and if it's too big, it's going to require a lot of cranking, right? So I just want to raise your awareness about that. So last couple pictures on this, kind of like this, your timeline. Everyone can understand this one. This is drawing bath water, right, in terms of symbols. So here you're running bath, and say you have your hot tap. So the idea is that it's off, now it's on, right, and you're running all that hot water to fill up your tub, and it comes down. But the idea is that now you're going down, and it's your water temperature. It's really picking up, and say, ooh, that's too hot, way too hot. Your water level, of course, you're filling up the tub right here, and you're at that stage, say, ooh, I got to put on the cold water. There's your cold tap. And your cold tap comes in, it comes down like that, and say it gets just about right as you're bringing it down to the temperature. And now, basically, say, oh, it's too cold right there. I got to put my hot water back on. Hot water then brings it up, and then boom, you're so happy. The tub is full, and it's just right. No one does that, huh? Okay. All right, last slide on this. And what I'm going to do is I'm going to punch through this so we have enough time to take the quiz, because I want to give you the essential points of the Ergo program. And that is this. I love this thing. It's an example of visual displays. One of the best graphic pictures of all time, displaying a ton of information. What I love about it is that this is Napoleon's march on Moscow. And look at the number of troops. Over 400,000 troops this guy started out with. Visually, it shows you that. And he's working his way to Moscow. Remember back then, we also had what's called the mini cold wave, or they call the mini ice age. And we had that for a couple of years. And of course, this was like right in the zone of that mini ice age, where they actually would say the soldiers could breathe, and it was so cold that they could see their breath drop out of the air. Basically, that moisture freeze and drop to the ground. So it shrunk down. They got there about 100,000 men. You know, they lost over 300,000 in the process. And then you see that black line. That's the return. They're coming back. It got smaller and smaller as it came back. And this is what they started out with, and this is what they came back with. About 10,000 men. Can you imagine losing over 400,000 men just marching to Moscow, right, picking a fight with the Russians, and then coming back? And then at the same time, it shows you the temperature at each one of these places. They're taking the temperature and so on. Just an amazing graph that really shows you the impact of a very poor decision by Napoleon, and that's why he spent the remainder of his days in the prison, in a little bitty island. So, end of that. Okay, ergo programs, I'm going to go through this real quick, but there's 5 slides I'm going to circle I want you to know. There is a book in the library. I'm a co-author on the book, and so that's why I'm pretty familiar with this process. But there are 7 steps in this process. It's a primer, and of course it came out because of the Act, and the ergonomics. NIOSH's role is to satisfy our customers, surveillance, and so on. There are a number of reasons why the primer came out, and as I mentioned, I'm one of the co-authors. And getting right to it, this is what the book looks like. You're going to get it, and you can also download it with this website right here. And you want to follow the main steps, because the first half of the main text gives you information about it, and then the second half is toolbox, things that you can use. And the pathway are these 7 steps right here: looking for signs, setting the stage, training, gathering evidence, developing controls, establishing healthcare management, and creating proactive programs. So what are MSDs? Basically, we're looking at work-related issues that come up or made worse and last longer by work. The causes are very complex. So our first thing, we're looking for signs, determine that effort. Number 2, we're looking at what are the aspects in terms of overall safety and health program, what are the dollar benefits. Also, we want to look at the policies and resources out there. Motivations. Employee involvement is really critical in this process. You've got to include them. And training is important, job awareness, so on, issues that come up, calibration. You are, in terms of your training, now that you've had, especially if you've done a project, you're over here. Think about it. You know the general ergonomics issues. You can form awareness, instructions about training. You've done analysis. You've been involved in problem solving. So you really are a team of people that are informed and actually not only can see something, but come up with recommendations to make it better. Gathering evidence, health indicators and job risk factors. Medical is important in terms of follow-up. Also looking at the risk factors, reaching inside boxes, overhead work, and so on. And then this is a, did anyone recognize what this is? Place that makes caskets, right? So these are, a grave job for sure. And the idea is that this guy's carrying this. I said, why are you carrying this stuff around? And they said, well, that's because the way I've always done it. I said, put it on a cart for God's sakes, and roll it around. I said, these things cost you $15,000 to $20,000 a pop, right? And so you want to make sure it's in good shape. They said, well, you do have a point there because, as we put these things together, notice this handle right here? Well, if we go back to this first slide, look at this distance. Check this out right here. Basically, they're fastening the top and the bottom of the casket together, and because they have to reach out and do this, the screws are off, right? And so they just kind of drill it down, and when they close it, if it doesn't latch up, they said, oh my gosh, we got a problem. And so later on, they're using a hammer to straighten it out. They said, well, it only has to work once, right? That's have to worry about. So, and they put the rails on and so on. They staple the battens on, carrying stuff up and down, reaching overhead. All these things come into play. You've seen that guy. There's some science behind this. So notice that this is not magic or art, right? There's some science here. And then if we go down, analysis and so on, one of the things, setting, control. Hang on, guys. I'm not done. You might miss something. Developing controls in terms of back belts, good work practices, and so on. And here are some examples of what is and what can be done. So pay attention to that slide. And then finally, just simple controls like a stick, right, to move a lever. Simple controls here, in the healthcare management is very important. That's where the doctors come in. Then finally, in terms of being a provider, and this is the final thing. This is important because you're going to see this. This is the only one that's different than the other 6, and that is being proactive, right? In other words, anticipating you're going to have an issue and then preempting that by going out there and designing it out of the problem, prevention through design. So again, here's your pathway, those 7 steps. Each one, these are all basically intervention oriented. And this one here, that last one, that's prevention. Okay? And then that's it. And then there's a bunch of good stuff.